Okay, hi everyone, welcome back. I'm recording another probability distribution video. In this video, what I'm going to do is talk about the geometric distribution. So I think we're now on to our sixth or seventh type of probability distribution in this series of videos. I'll do one more after this, and then that kind of be the end of it for the time being. But today is going to be about the geometric distribution. So the geometric distribution is a discrete probability distribution, and it models the number of trials it takes before the first success occurs in repeated trials of some experiment or event where there's a given probability of success, like a fixed probability of success on each trial. So the geometric is used to model kind of latency until we see the occurrence of the first event. So it's similar to the binomial distribution, and the trials here are known as Bernoulli trials, like for the binomial distribution. And these are simply kind of random experiments or events where the outcome can be classed in exactly one of two possible ways, as success or failure. And if you'll remember from previous videos, that's not a kind of value judgment. The success could be likelihood of contracting some disease or something like that, depending on the outcome that we're modeling. So unlike the binomial distribution, though, the geometric distribution has no fixed number of trials. So you remember with the binomial, it was kind of how many successes in, k successes in n trials, or 5 successes in 10 trials, something like that. The geometric distribution is kind of the discrete analog of the exponential distribution, which we looked at in a previous video where we were talking about the relationship between that and the gamma distribution. And the exponential models the elapsed time until exactly one event occurs using a continuous probability model. Here, though, the geometric is a discrete probability model. So what I'm going to do in this video is I'll generate some data that follows a geometric distribution, plot the geometric distribution of that data, and then investigate probabilities for data that follows that particular distribution. And as I've said, it's a discrete probability distribution. So to investigate specific probabilities or probabilities of specific values, we'll use the probability mass function, or the PMF. And we can also use the cumulative distribution function, the CDF, to work out cumulative probabilities of it taking a certain number of trials or less before we observe a success at some given probability. Okay, so let's get started by importing some useful software libraries. I'm going to import pandas as PD, NumPy as NP. I'm going to import SciPy, the stats library from SciPy, so scipy.stats as stats. I'm going to import matplotlib and seaborn because we will create a histogram. Okay, so let's start by generating data for a variable that follows a geometric distribution. So here I'm going to use a sample size of 10,000 and a probability of success on each trial of about 50%. So probability of success P equal to 0.5. And this data will model like events such as flipping a fair coin or something like that. It can be used to model real-world events as well. But if we think of the flipping a coin example, it kind of helps. It's a toy example that kind of helps develop our understanding and intuition. So I'm also going to set a random seed so we can replicate these results. So I'm creating an object called geo_var, so geometric variable. Setting that equal to stats.geom.rvs. So I'm using the geom method. So this is geometric distribution, and the RVS, you've seen me use this before, the random variance method from SciPy. And what we're doing is we're passing the size of our sample, so 10,000 observations, the probability of success on each trial, 0.5, 50%. And like I said, I'm setting this random underscore state equals 12. I'm just setting some arbitrary numbers of random seeds so we could replicate these. And then this is all one line. We're kind of wrapping that in the geometric. We're saying generate random variables, random variates for a variable that follows a geometric distribution with this line of code. Okay, so let's, what I'll do is I'll create a cross table, so we can see the frequency counts for our 10,000 trials, showing how many times it took until a success was observed on each of the trials. So I'm just using a print. I am using Panda's crosstab method. As the index, we're using our counts from our trials, and the columns are going to relate to this particular geometric variable object. So this is our data we've just simulated, and I'm just wrapping that in a print function. So we get, so it prints out the table for us. So what you can see here in this table is that, so each of the outcomes is stated, 0 heads, 1 head, 2 head, 3 heads, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. Obviously 13 and 14 didn't occur. But what we can see in the above table is that in our 10,000 trials, just over 50%, so 5,052 out of 10,000 of our trials were a success. So we observed, say, a head on the first trial. Okay, and that would make sense given our success probability of P is 0.5. So if we were modelling flips of a fair coin, about 50% of the time, half the time, we would expect it to come up heads, and kind of just over half the time we have had a success on our first trial, essentially. So higher numbers of heads before a success occurs are obviously less frequent, but despite their low probability, they still are possible. So for example, on one occasion it's taken exactly 15 flips before. So we've had 15 tails in a row before, or 14 tails in a row before we've got a head on the 15th. Obviously 13 and 14 didn't occur, like I said, but you can see this, the kind of longer times or more trials before a success have a lower probability, essentially. So if we're modeling some other event or experiment where the probability of success was different to 0.5 in this case, so it was higher or it was lower, the shape of the distribution would change, and it would be influenced whether whether we increased the probability of success, or we knew it was higher, or if it was lower. We've seen that with other distributions as well. When we change certain parameters, the shape of those distributions changes. And the geometric distribution, it tends to take on a positively skewed appearance, with the need for larger numbers of trials before we see a success. That will occur less often and have lower probabilities, as we can see in the counts in this data set. And we can create a histogram to plot the distribution. So I'm using Seaborn SNS.histplot to plot the distribution of our variable that we simulated. And you can see there it's kind of got this positively skewed sort of tapering off, kind of sharply dropping off kind of effect there. We do have one data point at 15. Very high probability of seeing this probability of 0.5. It's got a high probability of seeing a success with very few trials, and it tapers off quite sharply. So given that, if we wanted to know specific probabilities for given values, we can use the PMF to check the probability if it takes a specific number of trials before we see a success. So here, if we stick with the coin flip example with a fair coin, so a probability of success with a fair coin 0.5. So 50% of the time it's half as likely to come up heads as tails if it's a fair coin. And we can use the SciPy PMF method and pass it 2 arguments. So the arguments are the number of flips we want to know the probability for, so K, and the probability of success, which with our fair coin is P is 0.5. Okay, so what we're asking here is what's the probability of it taking exactly 5 flips before a success is observed. So I'm using stats.geom.pmf. So we're basically saying we want, if we had a data that followed a geometric distribution, if we interrogate the probability mass function for that, what is the exact probability that it takes exactly 5 flips before our first success if our probability of success on each trial is 50% is 0.5, and we can see we get a value of 0.03125. So that's only about a 3% chance, a 3% probability that we'll see our first coin flip that lands on heads on exactly the 5th flip of the coin. Okay, and I guess that kind of makes sense if we look at our kind of plot here, like very low probability of it was having to wait 5 flips before we got our first success. So we can also, so that was the PMF. We can also use the CDF, the cumulative density distribution function, to evaluate what the probability is that it would take a certain number of trials or less before we saw a success. So to do this, we can use the SciPy CDF method. I've demonstrated this in other videos for other probability distributions, but we can use the CDF, pass in arguments for the number of trials and our probability of success for each trial. So here I'm using stats.geom.cdf. That's the only difference to above. And here what we're really asking for is, what is the probability of it taking 2 or fewer trials before a success occurs? So we've set k to 2. So what we're saying is, what's the probability we'll see a success on either the first or second trial? That it'll take 2 or fewer, given our probability of success on each trial is 0.5. And what we see here is we get a value of 0.75. So when we're flipping a fair coin, we'd expect a head to come up on either the first or second flip about 75% of the time. And if we wanted to know the probability of taking more than a certain number of trials, say more than 2 trials before we saw a success, then we can just take the complement of kind of the above CDF and calculate it by 1 minus the CDF essentially. So, and I've done that here below. What I've done is created a new object, say called more than 2, and we've used stats.geom.cdf. K is 2, P is 0.5 as above, so we know that equated to 0, that came out as 0.75. But then to calculate the complement, all I've done is 1 minus this object, so 1 minus the CDF value. What we see is it returns a value of 0.25, 25%, which is the kind of remainder if you subtract 0.75 from 1. Okay, so that was the geometric distribution. In summary, it's a discrete probability distribution. It's used to model the number of trials, the number of events that it takes before we observe a success of some sort, where each trial is independent and there's a fixed probability of success for each trial. Okay, the outcome of each trial models a Bernoulli process that has exactly 2 outcomes: success or failure. Remember, they're kind of value neutral in terms of which event contributes to success or failure. It depends on your kind of research question, I guess, what you're modeling. Further thing to note is the geometric distribution is the discrete equivalent of the exponential distribution. Remember, we saw that in a previous video. That's kind of a special case of the gamma distribution, where we're modeling it's a continuous distribution, the exponential, but we're modeling the amount, how long it takes before we see one event occur. Here we're using its discrete trials, so discrete events essentially with the geometric distribution. Okay, so that was just a little bit of information about the geometric distribution. I hope that was useful and interesting. Can be used to model lots of different real-world events. In the next video, I'll talk about the beta distribution, which is quite an interesting distribution. And I think that'll be the last in this series of videos for the time being. Okay, thank you for watching, and I will speak to you shortly.